Right, for 6.1 part 2, it's pretty much just more of the same thing, but we have a few more examples that'll be like what you will see in your homework. So these are good examples too. So in example 1 of 6.1 part 2, we're still solving systems of equations by graphing. So, and then after we graph it, we need to write your answer as an ordered pair. So we're going to be sure that we have all of our answers in x comma y form. So in example 1, they're both in slope-intercept form. The y is by itself. So we can go ahead and graph a -2 on the y-axis because this is our y-intercept. And then from there, we can count up 3 over 1 because remember, if it's a whole number, it is over 1. So we're going to go rise 3 over run 1. So from the dot, not from the origin, from the original dot, that's our y-intercept. We're going to go up 1, 2, 3 over 1 and put our next dot there. And remember, because it's linear, it is a pattern that's going to continue in both directions up 3 over 1. So we can go back to our original dot and go down 3 over 1 all the way. We're going to draw a line with arrows on both ends, and that line is done. Our second example starts at a y-intercept of +3. So we're going to go up the y-axis to +3 and put a dot. And then our whole number, -2, is -2 over 1. So remember that negative means our line is going to go downhill from left to right. So from this original dot, I'm going to go down 2 over 1. And I see that they will intersect right there. So I'm going to go ahead and bullseye that spot so I can find it easier later. But I'm going to continue the pattern down 2 over 1, down 2 over 1, down 2 over 1, all the way across the graph, going back up 2 over 1 the other direction also. Graph your line, arrows on both ends. The solution, remember, is the ordered pair where they meet, where they intersect. So that point is 1, 1. So our x is 1 and our y is 1, and that is our solution where they meet. Okay, example 2, our first one is in slope-intercept form, so we're going to graph that one by putting our first dot 4 on the y-axis at 4. And then from there, we have a negative, basically nothing in front of x, which is a hidden invisible 1. And remember, any whole number is over 1, so -1 over 1, so we're going to go down 1 over 1 because we need our line to be going downhill since it is a negative slope. So down 1 over 1, we're going to go back up 1 over 1 the other direction too, just so we continue the pattern. It makes a better, straighter line the more dots you put on it. Okay, let's look at our next equation. We have x equals 2. So it's really hard for kids to remember if an x equals 2 is vertical or if it's horizontal. A lot of kids forget, is it horizontal or is it vertical? So if you can't remember, there's two little things. The first one is if it's an x, then that means it will go through the x-axis at 2. So the only one that would be able to go through the x-axis and be at 2 is a vertical line. If it was horizontal on the 2, it would really be a horizontal on the 0. So we don't want to put it here. That's horizontal on the 0 on the x-axis itself. So if it goes through just the 2 on the x-axis, it is going to be this way. But let's say you forgot that and you can't remember which direction it is. It's a good idea to make a little mini table off to the side. And if this says x equals 2, then all of your x's need to be 2's. So if we just did a few, just really quick so that we could remember which direction it goes, it means x equals 2 no matter what. So you can pick anything you want for y, but x is always going to be 2. So if I just do some easy numbers like 0, 1, 2, go ahead and plot these points. Put a dot at 2, 0. Put a dot at 2, 1. Put a dot at 2, 2. And you can see that it is going to end up being vertical. That's if you forget which is what. So if it's an x equals, it's vertical. If it's just a y equals, it's going to be horizontal. Okay, so these two meet right here at 2, 2. So the solution is 2, 2. All right, problem 3, example 3. They're both already rearranged in slope-intercept form, so this is going to be easy to graph. Our first line is going to start at the 2 on the y-axis. From there, we're going to go down 1 over 1, just like before. If it's nothing, it's a hidden invisible 1, and we know it's negative, so it's going to go downhill. So down 1 over 1, all the way across your paper. And then again, I like to put the dots going back up as well. It just helps keep your line really straight if you're not using a ruler. Arrows on both ends. Okay, our second line, our first dot is going to go on the y-axis at -1. And from there, you're going to go down 4 over 1. It's a whole number 4, so it's over 1, and it's negative, so it's also going to be going downhill. So we're going to go down a little steeper though, 1, 2, 3, 4, and then over 1. And the next one's going to be off my graph. So I'm going to go back up 4 over 1, and I see that they intersect right there. And then keep going up 4 over 1 because our entire line needs to be going downhill, but much steeper. So they're both negative slopes, but they do still intersect, and they intersect at -1 up 1, 2, 3. So -1, 3 is our solution. All right, our last example on this side. Our first equation is not in slope-intercept form, so we are going to need to rearrange it to get y by itself, and y is almost by itself. The only thing we've got here is a plus 2x. So I'm going to subtract 2x from both sides, and then it's in slope-intercept form. So y equals, and I always put my slope first, so I'm going to put -2x first and then +5. And remember, you can't combine these because they're not like terms. So we are ready to go ahead and graph it. Your first dot goes on the y-intercept at 5, so we're going to go to the y-axis up to 5. And we have a -2 slope, so it's going to be down 2 over 1. So from that dot, down 2 over 1, down 2 over 1, down 2 over 1, all the way across your entire paper, and back up the other direction, just so that you can get a really straight line. Oops, well, as straight as you can get. Mine's not very good there. And then here we have a y equals. Remember up here, we had an x equals, and it ended up being vertical. So now we have a y equals. So we know it's going to be horizontal, but let's just say you forgot and you don't remember which is which. Make a quick little mini table, and if this says y equals 1, then all the y's need to be 1. And you can pick whatever you want for x. So I like to pick easy ones like 0, 1, and 2. And then you're just going to plot them. Put a dot at 0, 1, 0, 1. Put a dot at 1, 1, 1, 1. And put a dot at 2, 1, 2, 1. And then you can see that's where they intersect. And you can also see that this is going to end up making a horizontal line on the 1. It also, when it says y equals 1, means it goes through the y-axis at 1. Okay, so they intersected right here. That coordinate is 2, 1. So our solution is where they intersect, which is at 2, 1. Okay, let's look at the back of this page. This has a word problem, which I really like because this is a really good example of a real world problem where you would use systems of equations. So it says, if I can get it to show, Keisha and her friends visit the concession stand at a football game. The stand charges $2 for a hot dog and $1 for a drink. The friends buy a total of 8 items, and they spend a total of $11. How many hot dogs and how many drinks did they buy? So we're going to come up with 2 equations. I'm going to let the first one be items, and I'm going to let the second one be money. Anytime you're talking about, we don't know how many of each item we bought, but we know we bought some items, and I don't know how much money we spent, but I know we do know how much money we spent, but we know how much each thing costs as well. So one equation is going to be for items, and one equation is going to be for money. And you really need to decide which variable is going to represent what. I'm going to have hot dogs be my x, so x is my hot dogs, and I'm going to let drinks be my y. And it doesn't matter if you did this opposite, you're still going to come up with the correct answer. Just be sure you know which one is which. All right, for my items. I don't know how many hot dogs I bought, so X. I don't know how many drinks I bought, so plus Y, because X plus Y were both bought. We bought hot dogs plus drinks. But we do know how many total items we bought. Hot dogs plus drinks equals a total of 8 items. So we know it equals 8. Money. X is the hot dogs. So how much did hot dogs cost? $2. So 2X plus how much did drinks cost? $1. 1Y. And we know how much total we spent? $11. So again, that's how to set up your equations. What 2 things did you buy for a total of how many? And what 2 things did that cost each for a total of how much did it cost? Okay, so I'm going to take my first equation, x plus y equals 8, and I'm going to rearrange it to get y by itself so I can graph it. I'm going to subtract x, and now it is in slope-intercept form. I'm going to put my negative x first because that's my slope, plus 8. So we have our y-intercept is 8, so I'm going to put my dot at 8. And then we're subtracting a negative 1 over 1 is the slope, so I'm going to go down 1 over 1. So this is my first equation, representing the possibilities of amounts of hot dogs and drinks I could have bought. Okay, now I'm going to use my second equation, 2x plus y, or 1y if you want to keep your 1 in front of it, that's fine. And I'm going to rearrange it to get y by itself, slope-intercept form. And so the only thing I need to do is subtract 2x from both sides. So y equals, I'm going to put my negative 2x first, and then that's a positive 11. So I'm going to put my first dot on the y-axis at 11, and then I'm going to go down 2 over 1. So that's a negative 2 slope. And I can see that they're going to intersect right here. If I go down 2 over 1, I'm going to keep going. And so that I can draw a pretty straight-ish line. And I see that they intersect right here at 3, 5. So 3, 5 is the amount of hot dogs and drinks I bought. Remember, 3 is the x coordinate, and for x, I called it my hot dogs, and then 5 is the y coordinate, and I called my y the drinks. So how many of each thing did they buy? They bought 3 hot dogs and 5 drinks, because that is the solution, because that's where they intersected. So for that amount of money and that amount of items, it had to have been 3 and 5. Okay. Last 2 is a little bit different. This is systems of equations with infinitely many solutions or no solution. All we've done so far today and all the other problems, they have had one solution. That's where they meet. That's where they met. That's where they met. That's where they met. That's where they met. Even in the hot dogs and drinks problem, that was the one solution, 3, 5. But sometimes you'll have lines that never intersect, or lines that intersect everywhere. So let's check out how to do a couple of those. So the first one, I'm going to graph the first line, the second equation, because it's already in slope-intercept form. So I can quickly and easily spot what I'm going to do first. I'm going to drop a 1 on the y-axis. And then I'm going to go up 1 over 2. Remember, this is your rise and this is your run. So I'm going to rise 1, run 2. Up 1 over 2, up 1 over 2, go back down the other direction, down 1 over 2, all the way across your paper. Then you can draw your line in, arrows on both sides. Okay, this one is not in slope-intercept form, so I'm going to come over here and just quickly rearrange it so that I have y by itself. So I'm going to first add x to both sides. I'm going to bring my x over first and then plus 2. And then last step to getting y by itself is I need to divide by 2. Remember, when you divide a quantity, an amount added or subtracted by 2, you have to divide both sides by 2. So on this one, remember this is a hidden invisible 1. So it's 1/2 x. That is a fraction 1/2. So it's 1/2 x, and then 2 divided by 2 is 1, positive 1. So I'm going to drop my first dot at 1, which is going to be looking like they intersect there. But look what happens. My slope is up 1/2. It ends up being exactly the same as this one, up 1/2, up 1/2. So as you can see, they don't only just meet in those dots, they also meet in all the in-between spots, because as I connect my line, they are meeting everywhere. So all of the in-betweens too means that since this is the exact same line on top of the original exact same line, the solution is infinitely many solutions. So infinitely many solutions happens if the two lines, once you rearrange them, the two equations are exactly the same. Because if you graph them, a line is the same as itself, means it meets everywhere. All right, very last one. Again, I'm going to graph the bottom equation first because it's already rearranged for me in slope-intercept form. So I'm going to drop my dot at 3 on the y-axis, and I'm going to go up 3 over 1. So up 1, 2, 3 over 1. I'm going to go back down 3 over 1 because the next dot would have been off the paper. So down 3 over 1. All right, arrows on both ends. This top equation is not in slope-intercept form, so I'm going to write it down over here, and I'm going to rearrange it into slope-intercept form by dividing both sides by 3 to get y by itself. And again, remember when you're dividing a number being added or subtracted, an amount, you have to divide both terms by 3. So we've got 9x divided by 3, which is 3x. And then negative 9 divided by 3 is negative 3. So this is very similar to our equation here, but not exact, because our y-intercept was positive 3, and our new y-intercept is negative 3. So we're going to put our first dot down here at negative 3, and then we're going to go up 3 over 1. So let's see what happens here. Up 3 over 1, up 3 over 1, up 3 over 1. What you can see is that since the rates are exactly the same, they will never intersect because the slopes are going up and over at the same rate. So these two lines would be parallel, which means they will never intersect. So where's the point that these two equations would meet? They don't. So that means there is no solution.